Okay, like any problem, you should definitely try to work this out on your own before you look at the solution. Let me draw a quick diagram to get us started here. So we've got a toy car on a table, and it accelerates across the table before leaving the table and going into free fall. Okay, and when it leaves the table, the distance above ground is 0.85 meters. We know that the table is 2.5 meters long, and the acceleration along the table is 6.4 meters per second squared. Now, we have our equations of motion for constant acceleration, but there's two different accelerations in this problem, right? In part 1, the acceleration is to the right, and it has a magnitude of 6.4 meters per second squared. And then in part 2, it's in free fall, and so the acceleration is directly down with a magnitude of 9.8 meters per second squared. So we can use our equations of motion with constant acceleration provided we split it into two parts. And the final conditions for part 1 will equal the initial conditions for part 2. I'm going to go ahead and establish a sign convention that to the right is positive and down is positive. I like to try to make the direction of motion positive in problems if I can. It makes things easier. Alright, I think we're ready for part 1. We're going to consider the motion along the table. Now that I've drawn the diagram and I've started to set up part 1, again, if you haven't worked this problem, you should try to take it from here and see how far you can go. At least fill in the table here and check and see if your assumptions are the same as mine. And then pause it once or unpause it once you've done that. Okay, so along the table, the x displacement is 2.5 meters. It starts from rest. We don't know the final velocity. I know that the acceleration is 6.4 meters per second squared. I need to know that final velocity, so I'm going to use this equation to find it, the equation that does not have t in it. So that gives me final velocity of plus or minus 5.66 meters per second, which I'll take the positive value of that since it's moving in the plus x direction. Alright, and that's the final velocity for part 1, and that is also the initial velocity for part 2, the free fall part. So, let's go down and do that free fall part. Now, what we're looking for, ultimately, is two things. We're looking for how far away from the base of the table does it land, that delta x, how far horizontally does it land, and we're also looking for this final velocity vector here the instant before it hits the ground. So we need to find the x and y components of that final velocity vector, and then resolve those into a single individual vector. Since it's moving in a curved path, we're going to need to split this up into x and y directions and solve each one separately. So again, I'm going to make a little table for both x and y motion and start filling in what I know. Okay, at this point, again, I'll give you an opportunity to pause the video, and if you haven't already done this, I want you to fill in this table. Write down what you know and what you don't know based on what we've done already in our sign conventions, and then unpause the video when you're ready to check your work. So for delta x, I don't know that. I'm trying to solve for that. The initial x velocity is 5.66 meters per second. The initial y velocity is 0, right? Because it's initially moving horizontally. That's our initial velocity for part 2. It's 5.66 meters per second in the horizontal direction, plus x direction. Final x velocity will also be 5.66 because the x acceleration is 0. I don't know the x displacement, and I don't know the time of flight. Delta y is 0.85 meters. Notice that it's positive, right? Because our sign convention here is that down is positive, and so this 0.85 meters is a displacement. It's a vector. It has a sign, and that sign is positive in this case. The initial y velocity is 0. The final y velocity is unknown. The acceleration, again, is positive 9.8 meters per second squared. It's a vector. It has a magnitude and a direction. Downward is positive in this, so it's positive 9.8. Alright, so I guess the first thing I'm going to need to do is I need to find delta x. And to find delta x, I need to know the time. Well, I can find time over here in the y part of the problem. I can use delta y is equal to v naught yt plus 1/2 at squared. That'll let me solve for time. So I get time of 0.416 seconds. Okay, so now I can put 0.416 seconds here and here. That enables me to solve for the x motion. I can say that delta x is v naught xt plus 1/2 axt squared, which in this case is 5.66 times 0.416 plus 0, because the x acceleration is 0. So my answer there is 2.4 meters. That's how far it moves horizontally before hitting the ground. As far as the y motion is concerned, I still need the y velocity, which I can get using this. So, alright, that gives me Vy squared, which Vy is plus or minus 4.08 meters per second. And again, I'll take the positive value because it's moving down, and I've defined down to be positive in my problem. Now it's just a matter of reconstructing the resultant. So I have an x component. If I draw myself a little coordinate system, I have an x component that is 5.66. I have a y component that is 4.08, and a final velocity vector v like that. Therefore, the final velocity, the magnitude of the final velocity, is found with the Pythagorean theorem. I get 7.0 meters per second. And then the angle theta here is I get with the inverse tangent of opposite over adjacent, which is 36 degrees below, plus x. And I'm done, which is a good thing because I'm out of space.